Hi everybody, and welcome to this series NoSQL for the Relationally Minded. In this episode, we'll explore what a document database is, how to build one, and how you can design architecture for it. Now, almost everyone has heard about document databases, and possibly even tried using them. So the first thing I want you to do is forget everything you know about document databases. Make your mind a clean slate. This talk will go through some of the rationale behind them and cover them to a level you probably haven't looked at before, including how to build architectures around them. So please try to put aside what you already know and enjoy learning for learning's sake. You'll come out of it with so much more. Now on to the talk. Traditional databases are great. They're well known, with heaps of articles and tutorials for them, and they're a great basic workhorse. And their usual design is one of normalized data. By normalized data, I mean it is where you structure your data so as to remove duplicates and have only a single piece of data for each single piece of truth. So you'd only store someone's name in a single cell, and the same with their age, for example. The relational part comes in when the data gets a little bit more detailed. Let's take a database of names and addresses. The relational model might separate out people in one table and addresses in another table, and then use a joining table to allow multiple people to live at the same address and each person to have multiple addresses, all without duplicating data. It's a predictable, neat pattern, and we've all seen it before. And to help you use this normalized data, relational databases have this great feature called SQL, where you can join these normalized tables together in queries in all sorts of shapes, like this, which is superb because you can then be ad hoc with the queries you send your database, and it will just figure it out and optimize internally as you go to best deliver those queried results by caching, etc. And this is fine until the queries become too much, it starts to scale and begins to slow down. At this point, maybe we throw more processors or memory at it, but to be honest, this only works so far. And so instead of band-aiding over the problem, let's treat it at an architectural level in the database instead. We know performance is key, so how do we speed our database up? If your database is running slow and you're going to try optimizing it, where would you start? The slow part in the queries are the joins, including scans on non-primary keys, and to a lesser degree, fragmentation caused by store mutability on writes or large data sets. And so relational databases have indexes to speed this up. They project the data into specialized storage outside row data and then cross-reference it from there. But this doesn't solve the problem that the database still has to operate the join, and then afterwards the system needs that data to hydrate a DTO, especially where the DTO includes nested data like sublists of addresses, contact numbers, and other such related data. There's a fair bit of work that goes into hydrating objects that contain that sort of stuff when you can only use a flattened response like a SQL result. So is it even possible to speed this up? Let's solve this by instead asking what's the key job to be done here? What do we need out of this? When we send a query, what we really want is data in our application, likely somehow displayed to the user or used to inform some logic decision. So getting micro-focused on speeding up index performance and joining isn't really keeping this higher goal in mind. How then can we optimize instead at a higher level? Let's say we have a contacts app which has a search result entry like this on the UI. Each result item is made up like this, and so to load a single card, the database has to join 5 tables together. If you think about the number of CPU cycles and memory management it needs to do this for thousands of records, perhaps repeatedly as you typed characters into your search, each time rehydrating complex DTOs, it might sound like a lot of work. And it is. And what if we wanted to include the friends we have in common on each contacts card? The data for addresses may be a simple nested array, but relationships are n hops. The data is richer and more nested. Our query or queries will be exponentially heavier for the database to join as the tables begin to balloon out. Other more data-intensive UIs include things like time series data. Take this admin UI, for example, where the same data is presented to each user with some filter exception, so it cannot be easily cached and takes a heap of scan and compute to put together. I don't want to depress you here, but it's a hard job, although doable. One way we can help is by pre-computing some of the data for each row into simpler inline formats. Taking our contacts list example, here's how the people table could be pre-hydrated to include friends and address data, and in this way reduce join and hydration load. But the data in red is duplicated, either from other rows in the same table for names and avatars, or from other tables for addresses and relationships. In a typical relational database, this gets very hard to manage, as we have to update all these places every time someone changes their name or other data. It gets tricky to be sure of what the source of truth is. It's fast, but these pre-hydrated values manifest the cache invalidation problem. So let's solve that problem before we dive too far into document databases, as I've seen this cause problems for a number of teams I've worked with. Given we have these 4 rows, and our example Stephanie's name here is duplicated all over them, there's no single authoritative point it is defined. So we can solve the cache invalidation problem by instead storing the originating request as the source of truth by making it an event, putting it in an event store, and allowing it to trigger subscribe projectors to invalidate the cached data. Here, 2 separate projectors are responsible for the independent cached column values, one for the column for last name, which affects only the top row, and one for the column of friends data, which affects the other 3 rows. The event store allows you to hold the change as the single point of truth before projecting it out to the pre-hydrated fields. You could use a relational database or other store for the source of truth instead, but using an event store allows you to serialize your changes, which helps with projector concurrency when invalidating the caches. I have more information on this on my talk on event sourcing in my channel on YouTube. So that's how we can solve the cache invalidation problem needed when pre-hydrating results, as we'll need in a document database. And let's look at another underlying concern around document databases, and actually NoSQL in general, that around schemaless and what it means. This is probably the main myth of relational databases I need to dispel here, that they are usefully schemaful. The idea behind schemaful databases is that the database can have some understanding of the types you're storing to validate them and/or optimize their storage. To this end, most traditional databases provide a palette of primitive types that you can assign to fields such as bigint, smallint, varchar or nvarchar, XML and binary. But the truth is, they only add runtime checking to your data because they're not part of your domain code. Let's take an example of storing someone's name. In code, we might ensure it's a non-empty string containing only appropriate characters for the respective user's locale with no leading or trailing whitespace. And in the database, we'd represent this rich domain validation as nvarchar some value, not null. It's missing a bit of depth, isn't it? How about age then? In our domain code, we might validate it as an integer, for sure greater than 0, and perhaps less than 125. In our database, we would represent this richness as small num, not null. I feel like it's missing something, don't you? How about email then? Our domain code might ensure a format value depending on our host, and maybe only require the email if a contact telephone number is not specified. In our database, this brilliant validation is reduced to a runtime check if the string is not null. How about an address? Its structure, for example, possible state selections or resulting postcode validity and address fields, ideally depending on the country. In a database, we might store this either as a subtable with a bunch of nullable fields and potentially mismatched data, or we might just give up and store it as a JSON blob in a string field. And lastly, how could we validate and store a setting or any other complex union type? In our domain, we might hold the value as a union, which could have different storage and validation based on its type. In our database, we'd be reduced to storing this either across a bunch of nullable columns, perhaps one for each primitive value, which may have conflicting values in each, or we could put it in subtables, which may also have potential conflicts. In both these designs, we have no setting-specific validation, and in both options allow conflicts where a value may be stored as both perhaps red and the number 4 at the same time. So we can see that even in simple schemas, the primitive types baked into a database without knowledge of the target domain are woefully inadequate to ensure valid data. And we all know this. It's the reason we always write complex business layers around our data stores, to provide this validation, serialization, and layers of dehydration that the database cannot. And while we may say it adds another layer of protection against invalid data, we've all seen databases where perhaps in error a previous dev has stored a number in a string column or reused a field for something it shouldn't be used for. But what gets me is that we still assert that a database level schema adds a layer of protection, even though deep down we know it doesn't add anything our business logic doesn't already do better. Anything could be in the database. I could store my son's Christmas list in your address field because there's no validation logic. And it's not just this, but there's also a cost, right? You do all your validation in here and in here. So that means you've got twice the amount of validation going on, where one is already far superior to the other. So we need to ask, do we actually need to do this because there is a cost? Have you ever had to deal with collation issues in string fields? Or found that an integer over-provisioned or under-provisioned? Have you ever needed to extend a binary store? Changes impact multiple systems without compilation checks because the database is separate from the program, nor are there assertable tests on it. There is a cost in refactoring, and never more so than in a shared data store like a relational database. So the question really remains, now that technology has advanced over time, do we really still need to specify the schema in the database to help it optimize? And what would be the cost of not doing so? There's a superb quote from Donald Knuth: "Premature optimization is the root of all evil." But because refactoring is so hard, we are still forced to super-engineer relational databases to cater for unknown futures by specifying the fields up front in the hope that it will help the database engine correctly optimize storage, indexing, and retrieval in predicted future situations. But the only way we can really know what the user's needs are is via rapid iteration and exploring how alternatives best fit in a system. And how can we rapidly iterate when refactoring is so hard and we need to specify all our fields and schema upfront? There's a huge range of mature products now that prove we don't need to know the schema to let databases self-optimize based on query frequency, location, and load. So let's stop considering databases as either schemaless or schemaful. Schemas don't actually help, and they cost because of their centralized nature. What then should be the drivers behind choosing a data store? It should not be schema, which we've already proved is more usefully done at a wrapping layer. Perhaps it could be instead availability, reliability, which is the alignment between a database transaction boundary and the solution domain, or the richness and structure of data that can be stored and queried. So how can we build a database that provides these features as its primary driver? Let's do this now. Primarily, if we're a data store, we need data. And because we've seen a schema isn't much use to us, we might as well store this as a single blob. In our example here I've used JSON, but it could be BSON, MessagePack, XML, COL format, HDF5, or any other format that you might choose. But it's all our data in one bundle. Its validation can be controlled by our business logic, and so we'll store it in whatever format is the fastest possible way to persist and retrieve our particular data. Now in storing data, we are storing things, and we know that every thing has an identity. It's how we identify this from that. And in a database, it's how we identify what piece of data we are creating, updating, reading, or deleting. Identity must be unique, and we live in a world of scalable systems, so I'd recommend this uniqueness is dependent on something scalable like maths, rather than a single bottlenecking allocator. In building for scalable systems, it will also help if our identity is shardable too. Ideally, identity should be a unique string of bytes that's balanced to allow sharding. And lastly, it helps if identity is serializable to something human writable, like these examples of a GUID or a nano ID, as then we can use it in URLs, configs, and other references. So our database must store both data and identity. The third of the four things we'll need is version. We know that because joins are expensive and we're trying to move away from them, document databases can be considered as aggregate caches, which means that the data is duplicated between different document instances, like in our example, Steph Hope's name. With Steph, it meant we needed a source of truth prior to the document database, such as an event store or other database, which we could then consume and project out to the multiple places where a single fact was represented. If you're consuming a source of truth with more than one concurrent process, for example in a scalable group, you need the consumers to be able to detect when a write has already taken place, to do what's called a conditional write. And if you're using the document database as part of an eventually consistent design, it helps downstream services to relay on which version of truth is represented in each of the documents. And so it's important to store the version of the source of truth that was last written to each document within the document itself. It helps assertions and downstream services if these version IDs are sequential and predictable, so that they can determine if a previous fact hasn't yet been processed if transport is unordered. There's more information on this on my talk on event sourcing, but the short version is, try to keep your version identifier something simple and predictable, like an integer that increases by 1 each time. Lastly, although identity is what we'll use to target writes, we usually want to be able to search and retrieve by other fields across more than one item at a time. We can scan through the data, but it's much faster if we can project some known aspects of this data into specially targeted indexes, such as B-tree indexes for orderable data, geospatial indexes for location data, pattern matching and approximating indexes for narrative data, and so on. So how would you build a document database, and how are they generally built? Fortunately, these first two require a key value store, which is a really well-solved problem. There are several performant open-source key value stores now available, such as BerkeleyDB, Lightning Memory MapDB, LevelDB, and RocksDB. These differ slightly in the way that they interact with the disk, but they all basically do the same job as an in-memory B-tree or hash table. They allow you to look up a value based on a given unique identity and add sharding and read-write optimization on top of this. Most of these stores are internally append-only, using instead compacting later strategies, and so internally use their own system of versioning for their data. But for our case, all we need to do is store our own head version in the data blob itself, like this. Now, the responsibilities covered by a key value store are of storage and retrieval optimization and availability, and so to search across the values, we can project the key value store's underlying streams to any one of a number of dedicated external indexes, such as full text indexes, like Lucene, linked document, such as hypertext indexing, geospatial indexing, content-based image, audio, and video recognition indexing, and behavioral indexing, and otherwise. These components together, essentially a key value store and indexing on top of it, are all that makes up a document database. I'm hoping by now I've convinced you that document databases are a useful idea, in that they can greatly improve the performance of a system by storing deep data about aggregates that can be hydrated much more simply while still queried via a wide range of index lenses. So why and when would we not use a document database? As we've covered, one of the considerations around document databases is that by storing deep data on each aggregate, you are much more likely to duplicate data between documents. And so this means in using them, you often need to solve the cache invalidation problem. And often the best way to solve this is to store the source of truth outside the document database. But this means you'll need to consider the boundaries of transactions on those systems, because distributed transactions are tricky. This means you'll likely want to use events and an event store to feed your document store, as events represent persisted transactions. But you need to bear in mind this means you'll be designing for eventual consistency rather than atomic consistency. Not a bad thing, but certainly something to mindfully consider. For more information about eventually consistent architectures, have a look at my video on event sourcing. Next, because the data in each document is best if it's a pre-hydration of the DTO returned, if you don't know the DTOs you'll want returned, then you'll need to design your documents as you go. This isn't a bad thing, and I usually recommend it, but it does take a little work to build up the result document structure as opposed to a relational database where you can build your select results per query by just defining the query and letting the database do the hard work for you. So what you win in speed, you lose a little in needing the upfront work on each of your queries to craft the response document. And this brings me to the last catch, which is if you're coming from a relational world, you might not know the tech. Many document databases available have specific features and limitations as part of the design, sometimes based on whether they're using a read-optimized or write-optimized relationship between identity and value, and sometimes based on the scaling models they're using. Mongo, for example, requires some knowledge of the storage system if you're storing large documents, whether you need to use GridFS or not. Dynamo only allows index creation during table creation, so once you're set up, you're kind of locked in, and refactoring means migrating to a new table. Raven has superb documentation and support, but even so, there's still arguably less than the more mainline Postgres or MySQL. And these are really reasons to spike out solutions first, rather than avoid the tech. As with any tech you're learning, try it first before you commit to building on it for a given problem. So I hope we've covered how document databases can be extremely helpful, and as most of the providers offer a cloud-based tutorial right on their website, there's really no reason not to experiment and get to know them as their own thing, different from relational databases and powerful if used correctly. That's it. We've covered some of the issues with relational databases that lead to a need for performance, looked into how to do this with document databases in a safe, scalable way, discussed the 4 main components internal to a document database, and lastly looked at some of the common pitfalls around adopting and building for document stores. If you have any questions, feel free to reach out on Twitter or LinkedIn. I'll be glad to hear from you. For now, thanks for watching and happy coding.